Yes, I am glad to open our series of seminars of the Commission, the Local Universe. And today we have two presentations by Sergio Martin-Alvarez and Konye Su. So we are glad you joined our seminar, and let's see those interesting about the scientific work done in investigating our galaxy and universe. So Sergio, you are welcome to share your screen and start your presentation.
Cool. Perfect. Thank you. Thanks for having me. And thanks everybody for tuning in for today. Can you see the slides?
Yes.
Okay, perfect. Right, so I'm going to be talking about simulations of dwarf galaxies, and in particular trying to move beyond the standard physics that we usually employ, which translates generally to star formation and supernova feedback. And in particular, the extensions I'm going to be using are by accounting for radiative transfer, for magnetic fields, and cosmic rays. So I'm going to be studying this dwarf galaxy here, which is a classical dwarf. I'll say a couple of things about these things in a minute. But then I'm going to be comparing with observations of galaxies around us, right? And one of perhaps the most important observations that we're ever going to have is the number density of galaxies that we observe for a given stellar mass around us. Because again, this translates very well into understanding very linking theoretical basic quantities with observations of the universe. So for example, one of the things we want to do when we have all of our these for numerical simulations is to track this number density, and you can see that different lines here corresponding with different colors track fairly well the observation data. Of course, the idea then behind this is that you have your lambda CDM model, which contains a given proportion of baryons, and in principle, if you assume that for each halo all the baryons were converted into stars, you would get a number density that would track this. But of course, this is not what we observe. This is not what simulations do. What we actually think these days is that the amount of galaxies that you get in our universe per stellar mass is regulated by feedback processes emerging from the physics that occur inside galaxies. So on the lower mass n of stellar masses, what we believe is that supernovae regulate the star formation. And I'm going to be focusing on this, but of course, if you go to the higher mass n, what you tend to find is that we believe AGN in principle are responsible for the stellar masses of these systems. However, there is a question to ask here, right? The agreement or lack of agreement that most of our simulations have with these observations occurs in the absence of additional physics that we know are important. And when I say additional physics, I mean well-established baryonic processes that, for example, in the case of dwarf galaxies, could be radiative transfer, right, and stellar radiation. So the question is, why do we get agreement without this physics, or are these physics the reason we don't get agreement? And in particular, again, I'm going to be focusing on these dwarf galaxies. Dwarf galaxies just being everything with star masses below 10 to the 9. And in particular, for this talk, I'm going to be talking about this classical dwarf that is in between this 10 to the 7 and 10 to the 9 solar masses. Dwarf galaxies are particularly important because when you go to our cosmological model, many of the challenges that we face nowadays are actually based on small scales, and in particular, the local universe, right? Many of these problems could be missing satellites, the cusp core problem, or too big to fail, just on the rotation curve form of things. Of course, and in particular, perhaps at the very least for missing satellites, many of these problems have potential solutions within baryonic physics, right? I would argue that this one is already solved, and many of the others, for example, cusp core has this whole idea of feedback injecting slowly dark matter out of the center of galaxies, heating them up. But before we even want to tackle these small scale problems, the question is, at least from the numerical perspective, can we actually simulate realistic galaxies that reproduce the ones that we observe around us? And for example, just an example, there's many others doing this kind of work, but Matthew Smith simulated in 2019 these multiple different dwarfs. One of them I'm going to be simulating today, and with just standard physics, meaning again, star formation, conventional physics, right? Meaning star formation and stellar feedback. And what we tend to find is that when we look at the expected relationship between the stellar mass of a galaxy and the halo mass of hosting that galaxy, you actually get galaxies that have too high stellar masses compared with theoretical expectations and so on. Of course, numerical simulations have a solution for this. One thing you could do is you can increase the impact of feedback by basically boosting the strength of these feedback events, right? What you do is you basically increase the amount of energy that you dump per event or per stellar mass and so on. And then, for example, here the Nihao simulations, they actually capture quite well these halo mass stellar mass relationship by doing this. Of course, again, in the same set of simulations, by varying different physics and changing parameters, trying warm dark matter models, so on, what we find is that it is still very hard for our simulations to reproduce the different observations that we have of multiple observables. For example, in this case, we can look at kinematics, right? And what you see is that you can get things that fall on the rough area, but this spread is not really quite there yet. And these are just a few of the actual problems that we actually face when we simulate these things, because of course you also want to get right the metal enrichment, you want to get the typical shapes of galaxies, their sizes, you want to get their kinematics and rotation curves, whether it is turbulently supported or rotationally supported and so on, right? So then the question is, if we are getting these things wrong, is it because we are missing some well-known baryonic physics? And if it is, can we actually use this physics to solve some of the numerical tricks that we use nowadays to get our dwarf galaxies right? So I'm going to be talking again about these three components: stellar radiation, magnetic fields, and cosmic rays, for two reasons. Firstly, because we can now simulate them and include them in our models. And secondly, and perhaps causing the very first reason that I gave, because we know they are important, right? These are baryonic physics that are quite important for galaxy formation. In the case of stellar radiation, it is not only the fact that stars release most of their energy in the form of radiation throughout their lives, but also that they affect the interstellar medium of galaxies, and they can also interact with supernova processes, right? So for example, by providing you with an early form of feedback, stellar feedback, what you can do is you can hold star formation immediately after star formation occurs, and you don't have to wait for supernova events. And also then you pre-process the gas to actually produce a more efficient feedback. You can also quench your galaxies with radiation. And perhaps an interesting debate that is emerging in my eyes, at least nowadays, and I actually will show you my 2 cents and my results on this, is that stellar radiation might actually make your star formation less clumpy, and this would maybe make it more hard for your galaxies to eject gas in the form of alpha. So might actually lead to some sort of maybe positive feedback on the long run. When you go to magnetic fields, they have been advocated for a long while. In principle, they shouldn't really change the properties of your galaxies unless you go to very extreme models that we could maybe potentially roll out using that. But if you just look at smaller scales, magnetic fields at the very least reshape the multi-phase ISM, they transform the properties of gas, and they also change magnetohydrodynamical turbulence in the ISM, which translates that to when you go to these smaller scales, they actually contribute to star formation, to shape star formation, and so on, right? So they're quite important for our models to be accounting for them. On top of that, when you want to add cosmic rays, you need to have magnetic fields because they're going to be determinant in the dynamics of these cosmic rays. So cosmic rays are really gaining popularity recently because even though this was known for a long while, potentially even the 90s, but at the very least in the late 2000s, we think that cosmic rays can help us drive outflows from galaxies, and in particular continued cold, well, temperate and smooth outflows, right, from our galaxies, which might help you reduce the gas budget and in turn actually reduce the stellar mass. They also, in the new simulations, we're also finding that they affect the ISM of these galaxies, and then they interact with magnetic fields, which in turn interact with cosmic rays, which establish an interesting feedback loop. And then there is some work also pointing towards the fact that cosmic rays may even boost the deposition of momentum from supernovae as well. This might make it a little bit more important. So I'm going to be including all of this in my simulations, either separately or combined, to actually understand the effects. On top of that, so our simulations are done with the code RAMSES, and we include all the additional physics, meaning metal cooling, UV background, star formation, blah, 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 to get galaxies that are realistic. But then just to give you a bit of more detail on the different models, whenever I have magnetic fields, they may have either an astrophysical or a primordial origin. Whenever the origin is primordial, I'm going to use one of these two strengths of the field, which both provide with magnetic fields that are strong. They compare really well to the strengths that we see in galaxies around us. But this one in particular, the primordial field, is a bit more on the very strong end. And I was more interested in this to actually understand primordial fields. Then we also have radiative transfer following the Sphinx model. No, sorry, sorry. Following the Sphinx model. So the idea here is that the Sphinx simulations are these cosmological boxes with a relatively modest volume, but they employ radiative transfer on the fly to reproduce the reionization history of our universe. And they actually get a quite realistic reionization history. And then finally, for cosmic rays, we account for both diffusion and streaming, which implies two kind of kinematic dynamics for this component on top of the usual advection. And then for the coefficient, the diffusion coefficient, so this is perhaps a bit of a more interesting parameter that is more of a free parameter in simulations, right? Because first of all, most of us are using these days a coefficient that is a constant coefficient. And we choose this value of 3 times 10 to the 28 because it sits quite well in between what different groups of simulations are doing, as it should be in principle in agreement with most observations. But indeed, the fact that this is constant and the actual value is something that is a bit of a caveat that needs further discussion and consideration. I'm happy to even chat about this value later on if you on top of that, we have star formation. So when I mentioned star formation, the idea here is that we not only use this density threshold star formation, but rather go to very, very small scales. So we want to be more accurate. And the idea is we form stars in regions that are collapsing. That's kind of the very physical idea behind it. So whenever a cell has a gravitational pull that overcomes its thermal, magnetic, and turbulent support, then we allow star formation in the cells that cannot be refined further. And then according to the local properties of the gas, what we do is we account for, again, the magnetothermal turbulent properties of the gas in the environment of the cell to actually determine which efficiency of star formation this cell will have. So on top of that, we include a stellar feedback in the form of supernova feedback. What we do for this is we use a Thiessen-Kim's model. It's a mechanical feedback. The idea is that you put the set of Taylor solution if you have enough resolution. If you don't, then your grid is two cores. What you do is you actually employ a non-homogeneous injection of momentum in your neighboring cells. So on top of this, my stellar particles are going to have feedback on 3 additional forms. One is radiation, as I mentioned before. This is the Sphinx model. We account for radiation ionizing hydrogen-1, helium-1, and helium-2, which means everything above hydrogen-1 ionization. And then we can also inject energy with supernova events in the form of magnetic fields or cosmic rays. So whenever I do any of these two, what I do is I put a fraction of the actual total energy, which is the same total energy in all my models, into the supernova, into the different components, right, of the supernova. So for magnetic fields, we choose 1%, and the rationale behind it is because it gives you magnetic fields that are pretty much on the order of magnitude of what you see in the ISM, as well as to what you see in supernova remnants at scales of about 20 parsecs in terms of energy density. And then when we go to cosmic rays, we use this 10%, which is, again, pretty popular across simulations. The idea behind it is that it is well within this 20% that we believe is the typical maximum proportion of cosmic rays accelerating in supernova remnants, and 10% is quite standard, I would argue. So all of these physics, we pull them all into our cosmological box. It's a fairly large box or a fairly small dwarf, but we have a zoom of about 700 kiloparsecs. We use Planck cosmology, and we go down to a resolution of 7 parsecs and 400 solar masses for a stellar particle. But with all of this, we get all of our different models featuring the same dwarf with just many different appearances. And of course, we can also do look at this dwarf using MOX observations in optical, infrared, or radio, which are also going to be quite interesting in the future. So this is the table of all the simulations I would really like to explore in these talks, but I'm going to do it instead of going into detail, is I'm just going to group them into different sets of physics. Meaning that I'm going to go from no feedback to feedback, then I'm going to include different models of magnetic fields, and I'm going to combine these models of magnetic fields with radiation to finally have cosmic rays, radiative transfer, and magnetic fields all in combination. So my analysis will just simply go in order of increasing complexity through the different runs, and then maybe we can talk about the details about what each set of physics is doing. But with all of this, the question is, can we actually simulate dwarf galaxies? So going back to the beginning, I'm going to be studying again this stellar mass versus halo mass relationship. What I'm showing here is instead this baryon conversion efficiency parameter, which determines what is the fraction of baryons in a halo that are converted into stars. So then we can compare, for example, with theoretical models, such as the ones by Peruzzi 2013. The problem for these ones is that they apply for higher mass halos. So what I'm going to be doing is I'm going to extrapolate them to lower masses, which implies that this is just roughly the order of magnitude that we're going to be interested on, to like at least to be comparable to these relations, right? This Peruzzi 2013. So there is a bit more zoom in halo mass. I'm going to show on top of this the same galaxy at different redshifts, right? Which implies that you're seeing the evolution of the halo as it increases in mass and the time just goes by. So the first model I'm showing you here is no feedback. This does as expected. You form a galaxy with a high stellar mass, and your stellar mass just completely is not unregulated at all. It's completely unregulated. It just keeps growing, and eventually you get very high efficiencies that are in complete disagreement with observations. Then you can include supernova feedback, and as expected, the supernova feedback is really good in regulating the stellar mass. And we actually find that we fall pretty close to the Peruzzi 2013, which again is kind of the area we want to be, but not necessarily where we want to be exactly, right? Because this is an extrapolation, a heavy extrapolation. On top of that, what we can do is we can boost, as is often done, the stellar feedback. So we follow the Sphinx model and we boost our explosions by a factor of 4. And what you get is that you further reduce the stellar mass in your simulations down to a redshift of about 0.5. So before I even show the interesting models, what I want to point out is that I'm not going to be able to run most of my simulations further than redshift 3.5, which is what we ended up at the end for the final work. But what we did is we evolved some of these models that are a bit cheaper to redshift 0 or so. And we just show here that if you look at the stellar mass, the constant stellar mass line, which is this line here, these galaxies, once you have supernova feedback, they just evolve with constant stellar masses down to redshift of about 0. So we don't really expect much evolution between our high redshift dwarf and the final product that you get, because we're going to compare with local dwarfs, right? That's kind of the idea behind this. So we can include magnetic fields, and at low redshifts, really towards the end of the evolution, they don't really change the galaxy. So the impact occurs mostly at very high redshift. When you have normal or realistic models of magnetic fields that are not too strong, what we find is that we obtain some additional support in our galaxy. This increases the stellar mass. And then you need to wait for supernova feedback to hold star formation. And then all this feedback comes and you punch the galaxy down to this redshift. The primordial model does something a bit different. Again, I don't really want to talk much about primordial fields because they're a bit more complicated, but basically, and we showed this before, I think Karsten, Jet, and Sig has some work as well. What we find is that they delay star formation in our galaxy. When we add radiative transfer, the picture changes significantly, because one thing that our simulations were missing, again, is some early feedback from stars, right? So once you have this radiative feedback, what you have is you form stars and you can completely dissipate giant molecular clouds and stop star formation. So the effects that we saw before for magnetic fields completely disappear in the presence of this, again, because now you don't have the entire cloud collapsing. And if we just look at what happens with the standard feedback with other radiative transfer, which I'm showing in orange, what you see is that you, due to this early feedback, suppress star formation early on, but eventually end up with a very similar stellar mass. This is because now most of the gas in the galaxy is conserved through its evolution. When we add magnetic fields, we can see that again, the primordial model kind of pulls up the effect. The one that injects magnetic fields in here is kind of doing the same thing, but as you inject more and more magnetic fields, you accumulate more star formation and you get the radiative feedback to be more efficient. However, and this is going back to what I mentioned before, by redshift of about 6 or so, what we find is that due to a recent merger, all the gas falls back into our galaxy, and we just recover the stellar masses we were having before. So it is a bit in agreement with what Matthew Smith was suggesting in his recent paper. And it is that the stellar feedback actually makes your supernova feedback and your feedback in general more sparse and actually makes it less efficient in ejecting outflows from the halo. However, when we include cosmic rays, things are looking also even more interesting. So this one run with cosmic rays and magnetic fields only is completely quenched initially, so it's hard to see any effects. But if we go to the other runs where there is more evolution with radiative transfer and cosmic rays, what we see is that indeed cosmic rays preserve this low stellar mass and the gas actually out of the halo for a longer period of time. But however, once again, what we find is that by redshift 5.3, 5.4, there is a merger with a neighboring halo, and we increase our stellar mass to end up in this kind of Peruzzi ballpark again. However, these runs were tracking quite well the boosted feedback evolution through different through high redshift. And this brings me to my next point, and perhaps the first comparison of these results, and it is with the Sphinx simulations. So again, the Sphinx kind of captures really well the reionization of the universe by redshift 6. And so if I look at the halo mass stellar mass of this simulation at this halo mass bin at redshift 6, what we find is that our cosmic rays model actually reproduces exactly the stellar mass that the Sphinx boost model has, which implies that even though all other galaxies are within the spread, what you see is that the same galaxy going from non-Sphinx model to Sphinx model and to cosmic rays look exactly the same, which implies that maybe including cosmic rays and radiative cosmic rays in the Sphinx runs might actually give you the same realistic reionization histories without the need to boost the strength of supernova feedback. On top of that, we can also compare with local dwarf galaxies, right? An important thing to mention here is that when you look at dwarf galaxies, if you want to estimate their halo masses, there's a lot of different caveats and assumptions that go into converting their kinematics into halo masses. But Justin Reed did this work recently, and we can just compare with his estimates for this halo mass. So these are all these data points that you can see on top of here. And then the interesting aspect is that actually, if you look at our cosmic rays and radiative transfer runs, they are the ones that they approach the closest throughout the entire evolution, the halo mass, stellar mass of the local dwarfs, right? Because at early times, they have this lower stellar mass that is close to the boosted feedback, which is in good agreement down to redshift 6. But then as you go towards these higher halo masses, what we find is that the boosted feedback tends to have stellar masses that are a bit too low in comparison with the estimates for the local universe dwarfs, whereas our cosmic rays then go up again to this kind of area. So that's quite interesting, I would argue. But of course, we can maybe discuss a bit this further later if you're interested. I'm also going to show another set of different interesting results. Probably won't spend too much time, but if we just look firstly at the galaxy size versus mass relationship for the stellar component, because there's a lot of data in here to look at. We expect the typical effects. Once you include feedback, your galaxies go to lower stellar masses. But in general, what you see is that most of our runs tend to fall on the small size of the spectrum compared with local observations. However, once you include radiation and cosmic rays, we get runs that tend to reproduce a bit more the spread of these observations. I'm going to be showing error bars in general. They're not error bars. They correspond to the variance of the galaxy within the standard interval, right? Again, at 33.5. But there's not much further evolution later on, so we really expect that the galaxies will remain approximately the same. We can also look at kinematics. In general, what we can see, at least in the rotation, is that most of our runs tend to have rotational velocities that are very low. Once you include radiation, you actually get more coherent rotations up to about 10 kilometers per second, and actually in good agreement with the cyan points that correspond to isolated dwarf galaxies around us. When you go to the dispersion of the velocities, what we find is that in general, all of our runs tend to have velocities that are a bit too high compared with observations. This is kind of frequent for simulations, but interestingly, when we include cosmic rays, we get the lowest dispersions. And perhaps this is the only point in all the parameters I explored in the actual work. But here, it is certainly the case that the boosted feedback gives us a better match to the dispersions that we see in observations. Whether the support is rotational or turbulent, it's a bit of an easier quantity to reproduce in simulations. But in general, I would argue here that once you have radiation, you get systems that are more rotationally supported, whereas in their absence, you get some things that are a bit more turbulently supported. I don't really have much time to talk about outflows, so maybe just focusing on the mass loading factor versus the specific star formation rate. So of course, the caveat here is that some of our runs have star formation rates that are particularly low, and that actually drives you a bit high in terms of the mass loading rate. However, if you increase this mass loading rate for most of our runs linearly, what you find is that this relationship has a slope of a bit like this. So generally, all of our runs with a relatively high star formation rate or a star formation rate that is high enough compare well with this. Sorry, I don't have the legend, but these observations are from McQueen 2019 for the darker gray points and Heckman 2015 for the lighter gray. So in general, I would argue that the mass loading factors tend to be in agreement for pretty much all of our runs, but depend instead on the star formation rate of our galaxies. And then the final result I want to explore in here today is the metallicity or the metal enrichment of my dwarf galaxies. I'm going to use the stellar enrichment here. We also have studied the gas enrichment, but they actually look very similar. This is a bit of a busy plot, but I'm just really going to compare with the Kirby 2013 work in here. So these are measurements for local group dwarfs again, and what we see is that we would like our simulations to roughly be on this approximate area in here. And in general, whenever you include a supernova feedback, you go from no feedback to regulating stellar mass, and most of our models tend to capture the stellar metallicities quite well again. However, when we boost the feedback, what we find is that we are in a bit of a disagreement with these local dwarfs. So we really favor these more complete models. And then again, so I'm comparing all these things with Redshift 1, with Redshift 0 observations. But again, some of our simulations we evolved into Redshift 1 or to Redshift 0.5, I believe. And you can see that there is no significant evolution between the values that they had. Sorry, the panel is a bit squeezed. Maybe it's a bit hard to see, but you can just trace vertical lines. You can see the stellar mass has increased barely for this run and barely for this one. So there is no evolution for the runs that we evolved to Redshift 1 or Redshift 0. Therefore, we expect and we hope that the cosmic rays run wouldn't really evolve that much because there is not much gas supply to the galaxy. So overall, I see that I'm a bit over 25 minutes. I'll leave my summary up with the different conclusions, but just really point out again that supernova feedback in general is not enough to get realistic galaxies, dwarf galaxies, although it does a really good job in general. But if you include cosmic rays, radiative transfer, and magnetic fields, you actually find that your galaxies move towards, they move in the right direction, right? They just start to look a bit better. So this is a good encouraging sign, and I think it should just encourage all of us to start exploring all these additional physics in our simulations. We explore a lot of different things in the paper. Hopefully it will be out after Christmas. So if you're interested in this and you want to see more or read in more detail, keep an eye for it. I imagine in January you'll be able to see this. If you have any questions or comments when you see the paper or now, like just feel free to get in touch with me. But like in particular now, if you have any questions, please go ahead and I'll try to answer them. Thank you.
Thank you very much, Sergio. Indeed, it is very good to expand knowledges. Our commission covers quite wide field of research, and the field in which you are working is very interesting indeed. So far, other people are thinking about questions. You are welcome to raise your hands. I would like to ask, what about influence of galactic winds in your simulations and in the evolution computations?
Right. So what? Right. There's a lot of models in here, but in general, what we find is that the outflows, the winds that are galactic winds, right? Like the winds that we find out ejected from the galaxy in general tend to be very similar across the different runs. Perhaps the most interesting result, let me see if it's the one I have in here. The most interesting result for the winds is when we have, yes, radiative transfer. Because what we find is that the outflows in general tend to be very similar across all of our different runs. They're mostly hot outflows. But once you have radiative transfer, you have this warm neutral gas. We call it warm neutral gas to gas below 1000 Kelvin. So you eject the same mass, and it's quite important, right, to get rid of the gas to stop star formation. But radiative transfer in particular helps you drive colder winds in these smaller galaxies, which I think is also interesting.
So in smaller galaxies, winds are cooler, yes?
With radiative transfer, yes. Without it, we only get these hot winds that simulations tend to produce in general.
Okay, thank you. So a very mixing.
Hey, Sergio, thank you. That was an interesting talk. I think dwarf galaxies can be particularly difficult because so much can affect their evolution. I have a question on another complication, which is that dwarf galaxies tend to be nearby large galaxies. Can you comment on the possible environmental effects on the evolution of on the formation of the stellar component of dwarf galaxies, particularly if they're in the halos or of large forming other galaxies?
No, 100%. Yeah. Also, like just on the comment that you raised before even answering the question, 100% on the paper, we even stress this out. This is one case of one galaxy, one dwarf, and they are particularly sensitive to everything, right? So it's very complicated to make assertions about this. So we definitely need to simulate more systems. This is a very isolated, moving into the second thing, this is a very isolated system. So all the effects we see are very secular. This is just the actual physics. But indeed, if you had a neighboring big galaxy, then first of all, you would also obviously have, like if you're submerged in the halo of a different galaxy, being a satellite, or you have an environmental heating due to this larger galaxy, we probably evaporate a lot of your gas or have most of your gas stripped through different effects, right? So this might be quite important. Unfortunately, based on my work, I cannot comment, but what I would really say though is that maybe then other physics, such as radiative transfer from the light emerging from the main galaxy through a continued process, will help your dwarf evaporate this gas. And then cosmic rays, so the idea behind cosmic rays is that you establish this smooth pressure gradient, right, that can drive winds. So these pressure gradient would probably, emerging from the large galaxy, would probably also emerge, traverse your dwarf. You could also maybe even have the large galaxy contribute to drive winds from the smaller galaxy. So at the very least, indeed, environmental effects are very crucial. But I would also argue that in the light of that, these physics that I'm exploring, sorry, I'm pointing at my screen, but these physics that I'm exploring in this work might also be important to understand environmental effects as well.
Yeah, oh yeah, and it makes sense to begin working with an isolated galaxy
So
before you introduce more complications.
Yeah, if I can point that out, maybe this is advertising future work, but we are currently simulating a very large galaxy with high resolution. So the idea is that we'll get also the dwarfs around it, and we'll probably be able to start to study these things. So,
right.
Yeah, I think it'd be interesting to see what happens.
Look forward to seeing that. Thank you.
Thank you. Thank you.
So very good, very good. We are expecting for such work. And I am curious, when you look now to all those dwarf galaxies which are infallen to our Milky Way galaxy, can you say something about them using your models, or this is a separate work?
So, right, no, it's I haven't thought about. I should have thought about that. So I've always been thinking, what can I tell about my models based on the local dwarfs? I wouldn't really know, because I'd want to do, and we're trying to move on to this line. I'd like to do mock observations first, right? To actually put the observations and the simulations on the same footing. So that's one thing we're trying to do scientifically now with this simulation, which is I show you the pretty pictures, but there is no science behind it yet, which is this whole making mocks, right? Where was it?
So you are showing now something for us, yes?
Oh yeah, sorry, no, like exactly. Like it would be something like we can maybe hopefully use this to better study whether, like, you know, like one thing we could do, for example, is using these kind of images, you could try to, for example, reproduce what Justin Reed did to estimate the halo masses of the local dwarfs, right? And then see if the measurements from observations and the actual assumptions are correct. These kind of things you could do. But at the moment, I haven't thought about anything you could say for the local dwarfs in our universe yet.
Okay. Silvia Pellegrini.
Yes, thank you, Sergio, for this interesting talk. I was just curious about what is the physical reason for obtaining larger stellar rotation and velocity dispersion in your simulations.
Right. So I think there is the two of them. Sorry, let me see if I have the video here. I think the two of them kind of come from different parts, right? Like the rotational velocities being higher, I think is due to the presence of gas, more gas, because you have this radiative transfer not allowing the gas to escape the halo, and then your stars form in more coherent rotation. I think that's one reason, like behind this higher rotational velocities. In terms of the dispersion of velocities, this is something that I've been thinking about for a long while and discuss it with colleagues. It really seems to be the case that generally your like simulations just really struggle to get lower velocity dispersions. One reason behind this could be resolution. You could have particles that are too massive, and then just kinematically they're so massive that they heat up kinematically the other particles, and they just don't allow you to traverse this kind of 10 kilometers barrier, right? Which is what we seem to be finding.
So
it's interesting though, sorry.
In your simulations, at the end, one star is as massive as 400 solar masses.
Yeah. So, I mean, it's unfair to call them stars. I call them stellar particles, right? The idea is that they are like a bunch of
so these are rotation and velocity dispersion of particles, not
of the
stars.
particles. Yeah, exactly. Not the stars. Yeah.
Thank you. Thank you.
Yeah.
So the last opportunity to ask a question.
You can always drop me an email if you have afterthoughts. I'm very happy to answer those as well.
Yes, thank you. And tell for observers what they should do in order to help you in modeling. So thank you very much, Sergio. Applauses.
Thank you. Thanks for having me.